Arun, Rashid, can we start?
Yes. We are going to start now. Just let me. Actually, we were waiting for Hussein, but unfortunately, he is not able to get in until now. Got some technical issues. Just allow me a moment, yeah.
Sure.
All right. So we are going to start now. Hello everyone. Good morning from Malaysia. There may be some of the participants. We received requests from overseas as well. So I would like to welcome everybody. I'm Dr. Harun Rashid, the country representative of IEEE Power and Energy Society, in short, PES, Day 2000, PES Day 2020 in Malaysia. So welcome to IEEE PES Day 2020 webinar. Today, I would like to take this opportunity to welcome all of you to IEEE PES Day webinar. And today we have a very interesting talk from our speaker, IR Associate Professor Dr. Gobbi Ramasamy. I would just like to mention some of the housekeeping things first. Please keep your microphone mute, and if you have any technical issue with your internet, so please keep your video off as well, because Dr. Gobbi will be sharing his screen. And if you have a very good internet, so no problem, you can continue with that. And if you would like to ask any questions, I will suggest there is a chat box. You can just mention your questions there, and at the end of the talk, Dr. Gobbi will answer all of your queries. So before I proceed, I would like to welcome IR Associate Professor Dr. Gobbi Ramasamy. He's the Associate Professor in Multimedia University. A little bit introduction about him. Dr. Gobbi received the bachelor's degree in electrical engineering from University of Technology, Malaysia, and the master's degree in the technology management from the National University of Malaysia. And his PhD in the area of torque control of switched reluctance motor from Multimedia University, Malaysia. He has been associated with technical education for more than 20 years. He was an electrician and R&D engineer before becoming a lecturer in electrical and electronics engineering. He has supervised many research projects on power electronics, variable speed drives, automation, and domestic electrical installation. He is a project leader and member of various government research projects related to electric motors and drive system. He is a consultant providing solutions for many problems associated to electric motors and drive system for various industries. He has completed many energy auditing projects in industries. He has published more than 70 technical papers in international journals, conferences, and magazines. He is an associate professor in Faculty of Engineering, Multimedia University, Malaysia. His research interests are in reliability of electric motors, power electronics applications in energy industries, switched reluctance motor drive system, and solar power application. Dr. Gobbi is a corporate member of the Institution of Engineers Malaysia, a professional engineer with practicing certificate registered to Board of Engineers Malaysia, electric energy manager registered to Energy Commission Malaysia, and a senior member of Institute of Electrical and Electronics Engineering, IEEE USA. So welcome to Dr. Gobbi for his talk, Electric Energy Harvest Strategies for Electric Motor System in Industry. So now I will hand over to Dr. Gobbi. Dr. Gobbi, will you be sharing your screen? Your presentation.
Yes.
You have,
yes.
Right?
I probably have to give you permission.
Yes. I believe you are aware. Okay. Just give me a second. I thought I have already given you, but I'm sorry. All right. So you are the presenter now. You can start sharing your screen.
Can you see the screen now?
Still loading. Okay. There. Already there. Okay, Dr. Gobbi, you can proceed.
Right, thank you. So you can see the screen now. Arun, I hope if there's any technical issue, you can just interrupt me and tell me about that.
Sure. I will let you know. So you can proceed now. The screen is clear. Your voice is clear too.
Perfect. Okay, very good morning, everyone. So happy to see that there are about quite a numbers who came for this webinar. And today I will be taking about only 40 to 50 minutes talking about electric energy. And I actually introduced this new terms here. So, but then I will clarify it later. What exactly I meant with our strategics for electric motor system in industries. Okay. Mr. Arun has given introduction of me. I think that is very lengthy. In fact, so I'm now at the moment we are a little bit active in doing research on the energy related. So recently we are actually working on second life batteries for PV energy storage system. So that is the current project that we are working on MMU. Hopefully that in the future we can have more talk on that. Okay. So let's start with the presentation. As Mr. Arun has actually mentioned that if you have any questions, you can just put it at the chat, and then later after the end of the session, I will be going through one by one. Hopefully I can answer all the questions, right? Okay. Now, first, before we go further, I'll just give you some introduction as usual. That in industries, I think this is applicable, or this is true for most of the countries, as long as if it is a country that is the economy is so much related to or dependent on the industries. About 42, in Malaysia, 42% of the energy that is generated is actually consumed by industries, right? And if you walk into the industry, then if you look at their electricity bill, you will notice that, if you do a detailed study of where the energy goes within the industry, you will notice that at least minimum of 50%, if it is not more, that 50% of the energy that consumed by the industry is always comes from the motor system. So that is very huge, okay? Very huge, because we are talking about even 5% savings in the electric motors. That gives us a lot of savings for the industry, for the company itself. And also at the national level, we are talking about reduction in the generation. That means we are talking about reduction in the CO2 emission and so on. That's the reason why, if you notice, in Malaysia particularly, or in fact in all the other countries as well, the Energy Commission has actually worked on ways. Okay, they have come up with a lot of policies, even standards, which I will be sharing in this talk as well, that to look into how we can actually minimize the energy from the electric motor system, right? Now, okay, so in Malaysia, again, I want to share this. Again, this is a motivation why energy commissions are very particular. In fact, they are very, very concerned about reducing the energy consumption by the industry, particularly for the motor system, because we know that large amount of energy is being consumed by the electric motors. So because we see that in Malaysia, for instance, we are talking about most of the generation is coming from the gas use of our fuel. It's actually a gas and a coal. And you know that both of these are not a clean energy. That means there's a lot of environmental impact. There's going to be a lot of CO2 emission. And therefore, it is important for us to look at all the areas, okay, talking about energy efficiency. I think the whole world now is talking about energy efficiency. So when you talk about industry, number one in the list is usually the electric motor system, because as I told you that the bigger portion of the energy is consumed by the electric motor system. Now, Okay, so let me give you the definition of this, because in fact the hours strategy, I don't want you all to have a wrong concept of hours energy, because maybe you have you got a wrong point, wrong perception or wrong idea of why I put this word. In fact, this is actually a business terms. Okay, business people use this term. They call it hours strategy. Okay. Because when we talk about managing the motor system now, we are actually talking about a business. Okay? It's actually about business. We're talking about, at the end of the day, minimizing the costs, okay? Improving or increasing the profit margin of the company. So eventually, everything talk about a business plan, okay? So our strategic that I looking at this, because in the industry now, okay, when they approach us, they talk about, they say, hey, come on, you see, my bill now is 200,000 ringgit every month. And when we do a study, we found like at least 100,000 ringgit every month, you're actually paying out of just for electric motors. That means, if you look at from business point of view for the industry, of course they are producing something. They are actually producing product. They are producing some kind of obviously whether it's in terms of pieces or in terms of kilogram or in terms of liter, gallon, whatever. So they are producing some kind of what you call product, and that product obviously, in order for the company, the industry to stay competitive. Okay, stay competitive in the market. So obviously they're going to do some kind of benchmarking. All of them, they do that. So when they do benchmarking, obviously they are going to look at how do I stay competitive? In other words, can I keep my product value, okay, my wholesale value, so that the consumer or the retailers will actually come to me rather than my competitor. So the major contribution of this profit margin or the price of the product actually comes from the energy cost. It comes from the energy cost, and therefore they will be looking at this term called specific energy. Okay, they will call specific energy. This is not a new term for electrical engineers. Specific energy. So that means they want to know how much kilowatt hour I'm actually consuming for every one piece. It's not pieces, sorry. Every one piece that is produced, or every 1 kilo that is produced, or every 1 liter that is produced. Because if I can keep this minimum, that means I can either increase my profit margin, and therefore I will be able to stay competitive in the market. So this is actually a business plan. Now that means when we talk about our strategic, what the business people in the industry, because as an auditor or even as engineers in industries, what happened now? I think everyone will agree with me that as engineers, we come up with all kind of technology, all kind of solutions, technical solutions, and we always propose it to the people in industry who are the top management. And usually this top management, they are more concerned about the business money. Because at the end of the day, it's about profit margin and savings and profit margin. And therefore, when you talk to them, so obviously before you can actually propose something, so I'll be sharing today what are the options that we have, what are the things that we can do so that we can get maximum out of the motor system. Maximum. When I say maximum means I am actually looking at the ways to minimize this specific energy. That means if now currently you are talking about, for example, taking 1 kilowatt hour to produce one piece, can I reduce it to 0.5 or 0.7 kilowatt hour per piece? So I'm trying to minimize the specific energy, because when I do that, I can directly convert into a ringgit, into a dollar, and I can tell them, you see, when I'm doing this, I actually looking at this much of savings and this much of improvement in the profit margin, right? So our strategy is actually a business plan for either cancelling or reducing spending on a system. That means, in our case, when I say system, I'm actually referring to a electric motor system. Okay. Now, what I'm trying to say is that, can we do everything, whatever you're doing now? That means you just proceed with, for example, the same production rate. That means you still produce the number of pieces per hour, whatever the production rate that you have, but at lesser energy consumption by electric motor system. Can we do that? Yes. Then what are the options that we have? These are the things that I'm going to share in the next slide. Okay. All right. Now, obviously, in this talk, I'm only focusing on induction motor because 90% of the motors in industries users, they only use induction motor for many reasons. I think most of you, when I look at the names, are mostly electrical engineers. I think that I don't need to go into theory too much, because you know that induction motors are much simpler. You don't have a carbon brush. There is no relatively very low maintenance compared to DC motors. I'm talking about large motors in industries. So therefore, the best candidate for electric motors in industries, all the while, even today, is induction motor. So I'll be only focusing on induction motor in this talk. Okay. In fact, all the whatever the energy commissions are looking at, even according to IEEE 6034 and so on, they are only referring to mostly induction motor because this is the major one that is used in industry. Okay. Now, the first thing that we are looking at is I will be talking about two things. Okay, how to optimize or to minimize the specific energy. Number one is the use of high efficiency motor. Okay. Number two, I'll be talking about employing the variable speed drive, okay, or inverters or variable frequency drive, or variable speed drive, whatever that we are okay with. So there are two things that I will be focusing, because these are the two latest thing that people are like wondering whether I should do that or I should do this. Shall I change it to high efficient motor, or shall I install variable frequency drive? Can I save how much I can save, or shall I just don't do anything? So these are the questions that always come to us. So hopefully I can clarify that point. Okay. Now let us start with the first one, which is the high efficient motors. Now, when you talk about high efficient motors, okay, obviously from the word high efficiency, that means that particular motor will have lesser losses. So if we just look quickly on the definition or the equation for efficiency, we know that is the output power. So it's actually depending on the output power to input power. Output power for the case of motor is the mechanical power, and then input power is the electrical power, right? So the input power, of course, is the output power, which is the mechanical power plus the losses. So obviously, if we are talking about high efficiency, we are talking about zero losses, which is the ideal case, or less, the minimum losses possible, so that you achieve high efficiency. Or if you're talking about high losses, then you talk about low efficiency. This is something that we know. So high efficiency motor, basically, it actually, the way it is, the existing motor is actually optimized. The next slide, I'm going to show you the details, so that the losses is going to be minimized and the efficiency will be improved. Now, how they did that? Okay, how they did that? So what is actually high efficient motors? Why they call it high efficient motor? Now, if you look at a typical induction motor, now let's look at the losses. The losses, okay, out of 100% losses, if you notice, 50% of the losses comes from resistance losses. Okay, resistance losses means I squared R loss. So which is from the stator, because we have a winding there, and we have the rotor, which we have the winding there. So they have current flowing in both of the stator and the resistor, and therefore it produces the losses. So that actually is 50%. And then we actually have a core loss, because we have a laminated steel there, so we have a steel because that's the best magnetic conductor. So we have losses, magnetic losses always there. And then of course we have the bearing. Okay, we also have a fan, cooling fan, that we will actually contribute to the friction and windage losses. Then also we have stray load losses, which is due to the air gap usually. So what happened is the existing induction motor, they optimize it. Okay, how do they optimize? For instance, if you're talking about reducing the losses in the stator, resistant losses, stator winding, so they use a large diameter copper as a winding as a coil. Similarly, more aluminum at a rotor. All this will minimize the resistance, and therefore it will actually improve the reduce the losses. And for the core loss, what they do is, of course, they use a better quality steel lamination, thinner and high quality steel to actually minimize the core loss. Similarly, better bearings, quality bearings, and better cooling fan, which reduces the friction and windage losses. Similarly, they optimize the air gap to reduce the stay load losses. So when they do that, okay, when they optimize this, then they actually categorize that motor into, at the moment, the one that you can able to get it from the shelf. They categorize it as 1, 2, 3, 4. IE1, IE2, IE3, IE4. So this is under the IEC 6034. Okay, 31, 2008. Now, what is this IE1 motor? So the IE1 motor is the standard efficiency. That means, in other words, the motor that you have in industry now, okay, we will actually put them under the category of standard efficiency. That means this is not high efficient motor, but it's a standard efficiency, IE1. Now, when you say high efficiency motor, it starts from IE2, IE3, IE4. Okay, so obviously when they have three options here, the efficiency of, for example, IE3 is going to be larger than IE2. IE4, the efficiency is going to be larger than IE2. Now, how they do this? As I told you, the optimization, what they have done, improvement in terms of the design and the construction of the motor, induction motor. But then there's an exception. This exception that we have to understand that this is only true for the standalone motor. That means this categorization is only done for the motor alone. For instance, if you buy a motor and then you are actually connecting that to a pump system, okay, the motor could be a IE4 motor, which is a super premium efficiency, meaning it gives you high efficiency. But then if the motor, which is IE4 motor, is connected to a pump system which is not, or probably a low efficient pump system, obviously the motor system efficiency is not going to be super premium. So that means the entire system, motor system efficiency obviously should be lower. You cannot be categorizing it as IE4. So that's why when they categorize this IE1, IE2, IE3, IE4, it's only referring to the motor system alone. Okay, alone. Okay. So that's the point that we have to understand that. Okay. Okay. Now, move next. Now, again, in the graph format, so if you look at this is the efficiency and this is the power. Efficiency versus power. Power, the size of the motor, the power rated power of the motor. Now, if you notice, the first one is IE1. Then we have the second one, which is IE2, IE3, and the IE4. Right? It goes obviously, as you can see, IE4 gives you a bigger savings. I mean, more higher efficiency compared to 3, 2, and the 1. Okay, and we are talking about the smaller size motor. The difference can be about 10% in the efficiency, and the bigger size, of course, the difference can be about 2%. Okay, which is quite 2% of a large amount. Also a big amount of kilowatt. Okay. Now, in a tabular form, this is actually tabulated, which also you can just Google and get this from IEC 6034. Again, the power rating and for various poles, and we have IE1, IE2, IE3. So as you can see from here, okay, for example, if I just select 30 kilowatt, a 30 kilowatt motor, let's say we focus on 4 kilowatt for all the IE1, IE2, IE3. So you notice that for IE1 is 90.7, for IE2 is 92.3, and for IE3 is 93.6. Okay, so obviously you can see there is about 2% difference approximately. There is a difference of, there's an improvement in terms of efficiency from IE2, IE1, IE2 to IE3. Okay. Now, life cycle cost. Okay, this is something that, again, I told you that when we talk about energy efficiency or energy savings in industries, it is always about business, as I given you during the introduction. It's always about the money, business. Because unless you can convince the top management that there is a possibility of a huge savings in terms of money, I don't think you can even get approval to get anything done. It could be a wonderful ideas with a lot of things, but then if you cannot prove that there's a big amount of money in terms of dollar that you actually save out of whatever you propose, there's no way they are getting convinced. Now, another point that we have to look at, from the business point of view is that we will always forget about life cycle costs. And this is not new, but we always forget to talk about life cycle costs. Any system, in fact, any system that you are looking at, even mechanical or electrical system, that you have to now look at the life cycle cost. Now, what is this life cycle cost? Is you are not only looking at what is the initial cost that you're going to spend. That means the money that you're going to spend to, let's say, buy the motor or buy the new technology or buy the new system that will probably do something. Okay, but not only about the initial cost, and also not only about the maintenance costs, but it is also about the energy costs. Because as I have given you from the introduction, at the end of the day, the industry will be worried when they look at the electricity bill. Okay? The top management, most likely, they don't even go to the production line. But when they look at the bill, they get worried. They really get worried. And that is where they call for the meeting and say, hey, come on, we have to do something because the expenses are increasing. What will happen if the tariff goes up, for example? If suddenly the tariff goes up, then again, they are going to see huge hike in electricity bill. So that means this is the point, the life cycle cost. That means whatever that we are going to propose, we have to look at this as a life cycle cost. That means whether I'm going to propose to have the high efficient motors, or whether later on I'm going to talk about variable frequency drive, I'm going to install variable frequency drive, we have to look at a life cycle cost. For example, for instance, let's say today I'm going to buy this motor, IE3 motors. Okay? So when you go to the boss, your top management, and you tell me, okay, boss, I think I need to upgrade this particular motor from IE1 to IE3. Then the boss will ask you, okay, what is the cost? Okay, the cost will be additional 30%. That means if I buy IE1, it will be cheaper 30%, but then I want to go for IE3, which is going to cost additional 30%. If you say that, most likely your boss is going to say, no, why you worry? Just go and install IE1 because we want to save the 30%. Why you want to install? You want to spend the 30%, right? But then if you put it in the life cycle cost, okay, that means if you actually confirm that, by going for IE3 motors, which in the next slides I will tell you what are the do's and don'ts when you are selecting the high efficient motors. Let's say you confirm going for IE3 motors and you know that saving is going to be there in terms of energy savings, then you actually can calculate what is the energy cost per month for that particular motor that you will save. And then every time you buy a motor, you will be able to use the motor at least for average of 15 to 20 years. That means you buy today, and then if you calculate all the costs for the next 15 years before you dispose the motor, then you come out with a pie chart and you will get this kind of pie chart. You will notice that 97% of the cost is actually contributed to the energy cost that you are paying every month. Initial cost is only 2%, and the maintenance cost is probably about 1%. So why should we worry about initial cost? Because, if it is really, you can see a savings every month. Most of the time when we calculate is within 1 or 2 years, you will able to get back the 30% or whatever the additional cost that you have to spend for high efficient motors, right? So we have to look into a life cycle cost when we actually decide, okay, whether we want to go for high efficient motors or even the variable speed drive. Okay, let's go further to these high efficient motors. Now I'm going to talk about, okay, shall I upgrade all the motor that I have in industry to IE2 or IE3 motors? Shall I do that? Shall I blindly go to the industry and say, okay, fine, let's start the project. We change one by one all the IE1 motors now to IE2, IE3 or whatever motors, and we are going to see a saving. The answer is no, a big no, okay, because we have to understand a motor is not like, okay, for example, now you're using a fluorescent light, okay, 40-watt fluorescent light. Then I say, okay, now I'm going to change this fluorescent light to LED light, which is going to be giving the same lux with only going to consume 5 watt. Yes, that is straightforward. Because more or less, the light will consume about the same power all the time when it is turned on. Okay, so obviously you can compare 40 watt to a 5 watt. Obviously, your 5 watt is going to give you a lot of savings. But when it comes to the motor, remember, when you have 30 kilowatt motor, for instance, it is not going to develop mechanical power of 30 kilowatt all the time. It depends on the load. Okay, and if you look at this particular curve, we have the efficiency. Okay, the efficiency versus load of the motor. What are the load? The percentage of load we connecting the motor. If you notice, usually the optimum is about 75% for the motor, and it will be reasonably a good efficiency up to the full load. Okay, but then when you go below, especially when you go below 50 hertz, you will notice that the efficiency will start to drop. Okay, your efficiency will start to drop. Okay, that means just imagine. Okay, just do it. Okay, so just imagine if I am going to, all right. Okay, so let's say if I have a IE1 motor, which is operating at about 80%. That means here. Okay, this is the IE1 motor. Okay, now then I have another system which is IE3. Okay, this is IE3, the green one, but then it is operating at 40%. Let's say the load, that means that particular system, the load is so light, or in other words, the motor was actually oversized. That means it's operating at a light load. It's a light load here. That means you can see here, even though I'm using IE1, the efficiency is higher compared to IE3 motor because the load is actually low. Correct. So this is possible, and it always happens in industry because most of the time when we go into the industry and engineers, they are not aware about the loading factor or what is the loading factor of the motor at the moment, because all the while they see, okay, motor is running fine, but they are not sure what is the loading factor, whether the motor is driving 75%, whether the motor is driving 50% load. They have no idea about it. So when you don't have that idea, what will happen is, if you just blindly convert it to a IE2 or IE3, you notice that you don't see so much saving, or probably no saving at all. But then how you're going to justify the additional cost that you have spent to buy the motor? Then you cannot justify that. So before you even decide whether you want to go for high efficient motors, the first step that you have to do is to determine what is the loading factor. You determine. You look at it, where is your motor now? Where is your motor now? Okay, if you're operating at this region, of course you can actually see that by going for IE2 or IE3, you'll be able to see the savings, right? But we have seen many cases in industry that the loading is like 50%, 40%. We have seen many. Okay, so in that kind of system, when you're upgrading with the same power value of the motor, you will notice that you're not going to see any savings, right? So that is the big mistake that you are going to do. So what you have to do is you probably have to resize the motor so that the motor will be operating at higher loading condition, and then you think about going for higher efficient motors, right? All right. Now, in Malaysia, in fact, last year, December 2019, as you know that we have a minimum energy performance standard, MAPS. Throughout the world, we have MAPS now for most of the appliances. For example, in Malaysia, for TV, washing machine, aircon, if you notice, we have an Energy Star. So it has to be minimum 3-star, So that is the MAPS, we call it, minimum energy performance standard. For electric motors in Malaysia, we don't have. For most of the countries in the world, they already have the MAPS for the motors. But in Malaysia, in December 2019, which is just a few months ago, they have come out with this standard called MS2639, okay, which should be tabled in the parliament. It will be implemented this year, hopefully. Then what will happen is they will stop. The custom will actually stop all the import of induction motors which is less than IE2. That means minimum induction motor grade should be IE2 after the implementation of this MAPS. Okay, so yeah, it is almost there. It's going to be implemented this year, but the other countries, including Thailand, Singapore, they already implemented this many years ago. I think even India, they have their own system. China, they have their own system. Some countries, in fact, most countries, the minimum energy performance standards is IE3, not even IE2. Malaysia, actually, we are talking about IE2, right? So that is about a little bit on the high efficient motors. Okay, what we should do, how do we select them, and so that we can actually optimize the specific energy. Now, second one that we, in fact, in industry that everyone is opting now is what we call a variable frequency drive system, because they want to again save energy. Again, we are talking about minimizing the specific energy of the industry. Now, very quickly, let me go through this pump system. So this is actually a pump system. Okay, you know that pump system is usually used to transport, let's say, a liquid, let's say, for example, a water from one point to another point, one place to another place. And usually the pipe system will have what we call a valve. You will actually have a valve, a mechanical valve, to control the flow. So when you look at a curve here, this is the pressure versus the flow. So the pump curve, if you look at the red line here, okay, the red line here, okay, you can see the red line here, which is actually the pump curve. Okay, when you are selecting a pump, you will the pump manufacturer will give you this curve, pressure versus flow, and this is the pump curve. Normally, when we design, of course, we will have a system curve, original system curve. So we'll be designing it for one particular design flow rate, okay, design flow rate. So that means, let's say we are actually designing at this particular point, okay, then what happens is, okay, then once we have decided, we will install the pump and we start to operate the pump. But then when you operate the pump, usually we don't run at this particular flow. Usually we'll be running at reduced flow rate. And let's say over here, this is an operating flow rate. So obviously when you reduce, how do you reduce the flow rate? By controlling the mechanical valve. So you actually control the mechanical valve to reduce the flow rate. So when you reduce the flow rate, then your operating point is going to be here. So this is the pressure, this is the flow, and it's proportional to the power. The mechanical power developed by the pump system is going to be proportional to pressure and the flow. So the shaded part here is actually this area for the power. Okay. So we know that mechanical power is given by the torque and the speed. Okay. In this case, even though you reduce the flow by reducing the what you call the mechanical valve, you will notice that nothing much in terms of mechanical power is going to be about the same, because the pump, the motor is still running at a full speed, because you don't actually do anything on the speed, but the flow rate is actually controlled by using a mechanical valve, and therefore there's no much changes in the speed. Torque more or less is going to be there. So you might have more losses because the pump is running at a full speed. So you are talking about more or less, there's no much reduction in terms of electrical power. Okay, or no, you don't see so much. So it's going to be almost same whether you're operating at this flow rate or this particular flow rate. Okay, this is what will happen. Now, instead of that, if let's say I connect a variable speed drive or variable frequency drive to this pump system, in this case, what I do, same thing. Originally, I select the pump system here, pump curve. Okay, I design the operating curve here with a certain flow rate here. Now, what I do is I don't control the mechanical valve. I actually fully open it. I don't control this. Okay, it's fully open. Now, what I do is I control the speed of the pump to control the flow. That means I still work at the lower, reduced flow rate, but by reducing the speed of the pump. When I do that, basically what happens is the pump curve will be shifted. As you can see here, the pump curve will be shifted. All right. Okay. Maybe a different color. Sorry. So if you notice, the pump curve will be shifted. Okay. The pump curve is actually shifted. Why it is shifted? Because we control the pump speed. Okay. Because this particular curve is only true for that particular speed. So once you change the speed, of course, the pump curve will be moved. And therefore, what you see here is that, your operating point now is here. And again, if you notice, the shaded area is going to be smaller. That means the mechanical power is going to get smaller. Okay, as you can see here, the mechanical power is actually reduced. That actually will reduce the electrical power. So this is how we actually save the energy. Okay, this is how we can actually save the energy in electric motor system. But then provided you have, the system where it requires some changes. In this case, there's a change of flow. Then yes, okay, the application, the pump system in this case requires change of flow, and therefore variable frequency drive will definitely help you to save on the energy. Okay, right. So as this is as everyone will know, as far as the what you call induction motor is concerned, we notice that every time you change the supply frequency, that means we change the supply frequency to change the speed of the induction motor. Every time we change the speed, the frequency or the speed, we see that power is also proportionally reduced. Okay, proportionally reduced. Okay. In fact, I think this is also the mechanical law, the PEN law or the pump law, affinity law. It always applies to most of the system. In Malaysia or most of the country in Malaysia, 75%, okay, almost 70% of our load is a pump load, followed by fan, followed by compressor. So that means all of them will actually comply to this affinity law, because all of them are centrifugal machines. And what is affinity law? As we know that affinity law says that when there's a reduction of the flow, when there's a reduction of the speed, proportionally your flow is going to be reduced, proportionally. And similarly, when you have a reduction in the speed, you have the reduction in the pressure with the relationship of square here. Okay, reduction in the speed square. And the most importantly that we have to look at is this. When there is a change of speed, and the power reduction can be a very huge reduction because the relationship is skewed. Can you see that? So there means a very little reduction. I will show you some case study where we have tested this just to give you actual data. When we reduce a little bit of speed, sometimes, for example, if the motors are always running at 50 hertz all the time, and then we just reduce it to, let's say, 45 or even 46, that means reduction by 4 hertz. We see a very huge reduction in the power, okay? Because most of the systems are palm and fan system, which complies in this affinity law is always true. Okay, that actually gives us another motivation that, we should find a way, if there is a need to change the speed, because like the case of palm system is now, then we should find a way to reduce the speed by using the variable frequency drive, because there could be a huge amount of savings, okay, in the power or eventually the energy. Okay, VFD, I won't go details into this because this is, as you know, the typical variable frequency drive. It's completely a power converters. Okay, it comprises of rectifiers as well as inverter, major components. Obviously, there's a lot of other issues. So the reason why I show you these slides, I will actually conclude in the last slides later that, we also have to look at, you have to understand one thing. If you think that variable speed drive is not going to give you savings, please don't install variable frequency drive, because there's going to be a lot of maintenance issues. That means there is going to be a lot of maintenance costs, okay, that is going to come in when you install a variable frequency drive. So you need to be able to justify. If you just install a VFD and you are not sure there's going to be a saving, please don't install it, because not only you're going to see no savings, but then you're going to see an increase in the maintenance costs. Okay, because since variable frequency drive is completely an electronic system, and just imagine electronic system in industry with all kind of environment which is very hot, very poor ventilation, very dusty environment. Okay, a very harsh environment, this electronic system can have a lot of failures, a lot of downtime. So it is not easy to maintain variable frequency drive. Okay, right. Now let's look at a case study. Okay, so this is actually one which is a real system that we have done. We have, and it's a good example to show you the do's and don'ts. Okay. Now look at this motor. This is actually about 200 over kilowatt motor, huge motor, and it is connected to a clutch. Okay, as you can see, there's a clutch here. The motor is connected to a clutch. That means it can engage and disengage. That means normally when the motor starts, you notice that the clutch is always disengaged. That means motor will be running or starting with more or less no load condition. Then you have a gearbox. Then of course the load. The load is connected to the gearbox. So when you have this kind of system, you have to understand one thing that it looks like there are a lot of questions there. Okay, fine. Thank you. Okay, if you look at this, you have a gearbox here. And then obviously, when we have a gearbox, we must understand that this is like a mechanical transformer. Gearbox is usually installed. That means they already calculated, they already designed from the day one that they want to achieve certain torque at the load. That's why it's running at a lower speed. So they already calculated what is the speed and what is the torque requirement at the load side. So accordingly, they size the gearbox. All right. So that means everything is already calculated. So if you are having this kind of system, now the question is that probably I want to throw to you: should we go for variable speed drive? Okay, initially, it was not connected to a variable speed drive, but should we go for variable speed drive? That's a question. Okay. Okay. Whether it is true. So now, if we measure the current, okay, we actually measured the current for this particular system. Now, if you notice, it is drawing about approximately 290 amps. Approximately, you see that the current is about 290 amps. Okay, sometimes it drops, but it's always about above 200 if you notice. But of course, sometimes you notice that it drops to about 14 or 15 amps. But why this is drops by this? Because when they see some issue with the product, automatically they give a instruction for the clutch to disengage. When that means the motor will be running without load, and automatically we see the current will be dropping to about 14 amps. But then again, when the clutch is engaged, and again it shoot up to about more or less 290 amps. Now that means the load, more or less, if you notice here, the load is actually a constant load. Okay, so it drops to 14. That is because there's some defect into the output because of the soil moisture and so on. Okay, so more or less is a constant load. So now the question is, shall we go for VFD for this particular application? Okay, shall we go for the VSD in this case? In fact, this particular industry, some say no. Thank you. No, by right, no. But then this industry actually they install a VFD. Okay, that's why when someone approach you from the industry, especially the salesperson from variable speed drive company, you please be careful with these people. Okay, they will actually come and convince you, and they will say 30% saving. I have no idea until today why 30%. Okay, why they always use the word 30%. Okay? They will always convince you, say, oh, no issue, we can reduce 30%. In fact, these things happen to this company. They convince the boss and they install the variable speed drive for this. And what they did, they actually set the frequency to 48 hertz. Okay? Remember, this is a more than 200 kilowatt motor. That means the VFD was about 500 horse power. Okay, 500, huge, very huge. Okay, that means they spend a lot of money and they have to place the VFD in a special room with air conditioning. And then they set the frequency to 48 hertz. Why they cannot reduce more than that? Because as I told you just now, if you reduce the speed here, you are going to give a low speed here, which is going to have an impact on the load. So what they did is they just reduce it a little bit by 2 hertz, assuming that, okay, we can see a saving. But there is no saving at all. There is no saving at all, because eventually after about 1 month, the company has actually complained and they actually bring this back to 50 hertz. That means now this particular system is running with a VFD at 50 hertz as normal. That means you have to maintain the VFD, you have to pay additional cost for the air conditioning system, you have to maintain this VFD, which is additional maintenance cost with zero savings. Okay, this is actually example of a bad example of where you should not be using the VFD. So that means not all the motor systems should be connected to the VFD. Okay, case number 2. This is again a fan. It's actually an exhaust fan. It's an exhaust fan. Also huge. It's about 120 kilowatt motor, running 24 hours, 24/7, 365 days. And is one of the bottlenecks for the industry. It means if this stops, everything stops. I mean, your total production rate is going to be affected. Now, what we did was, yes, this particular motor is already been connected to a variable frequency drive, and we did something. Okay, all the while they are running with 40 hertz. Okay, this is again happens in industry. They already installed VFD, and then they probably already preset certain frequency. And then when we go and ask the technician and engineers, okay, why 40 hertz? They said it's already preset. You're not allowed to change it. But it's not true, okay? So what we did was, we actually did some study. Okay, fine. We say, okay, let's do a study. Okay, we hooked up our power measurement meter before the variable speed drive, also the after. So you will notice few things here. Number 1, if you notice, when it is running at 40 hertz, in fact, we try to push to 50 hertz, we notice the power is more or less about less than 30 kilowatt when it is running at 50 hertz. About less than 30 kilowatt. But the motor is 120 kilowatt motor. That's huge. That's huge. That means, as I told you just now, this motor is actually driving about 30% loading. That means it's running at a very low efficiency all the time. All the time. 120 kilowatt is taking only about 30 kilowatt when it's running at 50 hertz. Okay, that's number one. The motor is oversized. It's running at a light load. Number two, if you notice, it is always running at 40 hertz. So what we did was, we said, okay, let's reduce the frequency by 2 hertz. Let's run at 38 hertz. And then we found, wow, look at the reduction of the power. From 24.9, it reduced to 19.9 just by reducing 2 hertz. That means in this case, there is no additional cost involved because VFD is already there, motor is already there. You just have to go there and just do some simple settings, and then reduce it to 2 hertz. And immediately you see that reduction in the power. And we see that the system works fine. 2 hertz makes no difference in terms of production rate. But then in terms of energy saving, there's a huge saving. As I said, it's 24/7, 365 days. Okay, so what we suggest in this case is, of course, it's a good thing. We say you must optimize the frequency, see whether you can reduce further. Number two, the motor is completely oversized. If you can reduce the size of the motor, probably you can have better efficiency. You can further reduce the kilowatt in this case. All right? So this is exhaust fan that I mentioned just now to you. Okay, as a conclusion, okay. So as I mentioned to you that when it comes to motor, it is a dynamic load. You have to understand the efficiency depends on the loading. Okay, and therefore high efficient motor should be a secondary option. Okay, don't blindly change it to high efficient motors because it may not give you any savings. Okay, so you have to look at a loading condition first. Make sure that you optimize the current system. Make sure that it runs at 70% or 80% load before you think about going for high efficient motors. Okay, as I told you, I show you in the curve that IE1 motor can be more efficient. They can be more efficient than IE2, depending on the loading condition. Major issue in industry is maintenance and understanding on the motor system. So they don't understand what is loading factor. They don't understand the ventilation is important. The environment, okay, is important. The cleanliness of the motor is important. Otherwise, the cooling motor get heated up. That will increase the losses. That means everything contribute back to the energy and engine. Okay, so VFD can minimize specific energy, yes, provided it is installed into a right motor system. Otherwise, it could be additional cost to the company. So, in this talk, I've actually talked about considering high efficient motors and a variable frequency drive in order to minimize the specific energy. How can we minimize the specific energy to help the industry to stay competitive, to improve on remember, the tariff will go up. The tariff will go up. That means if the business is done as usual, the only way for the company to sustain is to increase the product price, which means put them in disadvantage in terms of competitiveness. So in order to stay competitive, in order for them to keep the product as low as possible or maintain the product price, when there is an increase in the tariff, they have to compensate by reducing the energy usage. So, energy efficiency is the answer to that. Okay. With that, thank you. I'm done. Aaron?
Thank you very much, Dr. Gobbi. I would like to open up now for questions, but we have a number of questions in the chat box. So maybe I will read one by one. Okay, there is a question from Dodi Ismoyo. He mentioned that on your slide 2, there is no source from renewable energy, excluding hydro on that table. Maybe you would like to comment anything on it?
The slide number 2. Oh, okay. You mean excluding? Oh, no. Yeah. Okay, this is actually the table that we get from the Energy Commission, actually. Of course, renewable energy, if you notice that we are still at the very low in terms of electricity generation mix, we are actually talking about less than 5% at the moment, even though we are pushing for 20 to 25% or even 30%, but at the moment it's still low. So hydro, as you know, is also included into the renewable energy, for your information. Right, so that's why it is, this table is actually taken from the Energy Commission. Probably when I take the latest one, I will add in the renewable energy, but as I told you, it is still at a very low percentage compared to the others, the gas and the coal in Malaysia particularly. I hope I answered that question.
Okay, there is another question from the same participant. On your slide number 6, he wrote that you said one of the way to increase motor efficiency is to use large diameter copper. But isn't large diameter copper will create more loss due to skin effect? Isn't it we need to use smaller diameter of the copper wire but more quantities and in a standard configuration to have better efficiency?
Yeah, okay, actually, yeah, it's a good question. Now, when they say diameter, okay, not purely increasing diameter. In that case, if you increase the diameter, you know what will happen. The size of the motor also can actually go up. No, actually, it's the quality of the copper. Because if you look at the quality of the copper, you know, it's just like any metals. In fact, any metal that you take, you actually have a different grades. Like gold, you have different grades. Similarly for the copper. In fact, I think some of you asked question on that. You see, what happened is, maybe I will answer one shot. See, what happened is, this copper has a different quality copper, right? So obviously, you can have the same diameter with a different characteristic. I mean, same diameter with a different resistance value, with different losses. Okay, that means that's the reason why, you know, probably some of you will ask. I'm sure somebody already asked. If I buy IEEE motors, which has better quality, better quality copper, but then you send for rewinding and come back. You know, you buy IEEE motors, which has a better quality copper, so therefore you get a better efficiency. But then for some reason it burns, and then you send for rewinding and come back. So now the question is whether this motor is going to be same as IE2. The answer is no. Because when you go to, you know, I used to go and sit in the place where they do rewinding. If you notice, the person who do rewinding has no idea what they are doing. But they do as per instruction. Okay, they take out the winding out, they see the diameter, and then see the number of turns, and then they will take, and then they will do the same thing, and they put it back and get everything and run the motor and send to you. They never do any efficiency study. Okay? And then obviously, if you do the efficiency study, you will see the performance will drop, the efficiency will drop. Why? Because when they replace it, they don't replace, they will use the same diameter because they copy, but different grade copper. When you use a different grade copper, what will happen is, you will obviously notice that there will be a more loss. Okay, there will be a more loss. So, when I say a diameter, yes, the diameter is optimized, but it is more like the quality, the grade, the quality of the copper itself is a better quality copper to actually minimize the resistance loss in the data winding. Hope I answered that question.
Okay, there is another question from Srinivasan. He asked why Malaysia did not go for IES 3 standard.
IE3 standard. Srinivasan, you should ask the Energy Commission this question. In fact, we already asked. In fact, for your information, I hope nobody from Energy Commission here. We are talking about coming up with a minimum energy performance standards since 2015. For your information, right? We are working of coming up with a minimum energy performance standards for motors for Malaysia since 2015, and we are very slow because if you notice other countries like Singapore and the other countries, they already implemented maps much earlier compared to us, and we are yet to. In fact, for your information, what the standard that I mentioned to you is just a standard, but the maps is not it has to go through the parliament in order to be gazetted. That means in order to be implemented. So that means, in other words, Malaysia can still import IE1 motor into Malaysia, still, because it is not gone through the parliament yet. So we have to start somewhere. At least we start with IE2. Obviously, we should have started with IE3, but I think we should start somewhere, because most of the countries in the other world, they start with IE2, then eventually after a few years, they upgrade it to IE3. That means first they will stop all the IE1 motors coming to the country. After certain years, they will stop IE2 motors coming to the Malaysia, to the country. So I think similar will do. So we are just started. So obviously we cannot jump to IE3 at the moment. We start with IE2. Eventually, yes, it will be upgraded one by one. Thank you.
There is another question from Chio. Will the motor efficiency drop after rewinding the motor? Yes. If yes, what is the percentage of the drop?
Okay, I explained to you just now, because yes, definitely it will drop, because as I told you, the rewinding, they don't use the proper quality, the grade of the copper, sometimes the workmanship and so on. The drop in the percentage, we did some study. I cannot give you exact, but then it will be changing every time you send for rewinding for bigger motor. I'm talking about more than 30 kilowatt motor, bigger motor. We are talking about the drop between 3 to 5%. 3 to 5%. That's huge. I'm talking about huge. That means one time you go to rewinding and come back, your efficiency drop can be between 3 to 5%. Okay? So, yes, there will definitely be a drop in the efficiency.
There is another question. On your slide number 11, maybe you can share any rule of thumb for industries for them to understand better in choosing electric motors based on the motor efficiency or based on its size, scalability on their industrial load. I think it's more like a comment. I will move to the next one.
It's okay. What is the comment? Sorry? Rule of thumb?
Is there any rule of thumb or formula for industries for them to understand better or optimize in choosing electric motor based on the motor's efficiency, like IE1, 2, or 3, or based on its size, scalability, based on their industrial load?
Okay. Generally, what happens is the motor. We expect the motor to operate at about at least 75%. That is the optimum. 75% usually you get the best efficiency. So we always encourage people to go for 75%. Yes, if it goes higher, it's fine. But then what happens is, because we are also concerned about the maintenance, because it is always not good to work at the full load all the time, because overloading can happen. There will be a lot of maintenance issues. So usually, we encourage, when you size the motor, make sure the motor operates in average 75% or 80% of the load. That will give you the best efficiency.
Yep. Okay, there is another question from Kuweha. Is SEDA, S-E-D-A, SEDA, I think I'm pronouncing correct, also
SEDA,
play key role in addition to Energy Commission for energy saving?
Okay, SEDA, as you know, SEDA is more on the renewable energy. Okay, more on renewable energy. That means they are taking care of all the, you're talking about the solar, you are talking about all the renewable energy sources. Okay, but Energy Commission is actually taking care of everything, not only this, they're also talking about energy efficiency information. So because we have to understand that, you see, for example, I think everyone is now understand this. If you are planning to put a solar panel on top of your house, your roof, let's say 6 kilowatt, for instance, or let's say 4 kilowatt, you are planning to put a solar on top of your house roof, say 4 kilowatt. Now, before you actually, okay, maybe you say, okay, this is the amount of bill that I always use every month. And that means this is the amount of consumption, average consumption, how much is a kilowatt every average for my house. So therefore, I will install a solar panel based on the roof size. Okay, fine. But now, you must understand that before you even think about putting the solar panel, the first thing you should do is increase your energy efficiency in your house. Okay? For example, there are many ways in the house, for example. Number one, try to have a proper ventilation in your house to reduce your cooling load, your aircon load. Try to have curtains so that your sunlight is not coming and eating up your rooms, so that you know your cooling load will be reduced. You can have the LED lights with proper switching configuration. That means most of the houses now I see one switch, 4 lights. Okay? You can configure that, rewire that. You have one switch to 2 lights so that you can minimize on the electricity bill. Try to reduce use of kettle, for example. Try to use refrigerator with 4-star or 5-star energy. Washing machine, try to use once only at one day, depending on the load. Don't try to use, if it is a 14 kilogram washing machine, don't just put 5 kilo. Try to pile up for 10 kilo at least and then use it. And then, there are a lot of things that you can do to improve the energy efficiency. That means if originally you're using 4 kilowatt average, by doing all this work, which we call it energy efficiency, probably you can reduce 1 kilowatt there. So you only have 3 kilowatt. And then you install the solar panel of 3 kilowatt. Okay, so that should be the best way. In fact, we always push the last time Mastec. We said that energy efficiency should come first before you even propose the solar panel or any other renewable energy. Because why should you come out with a renewable energy, but then you are also supplying to the losses? It's actually a waste. So SEDA has their role, okay, obviously, but not particularly on the energy saving. They are more towards renewable energy, clean energy. Okay, but in terms of energy saving, in fact, the SEDA, and last time they call it MGTC, okay, Malaysian Green Tech. So what happened is SEDA was taking care of building. Okay, they were taking care of the building to do the auditing in the building. I think the Energy Commission requested SEDA to monitor the work, energy auditing work. So in that case, they also partly work on the energy saving. But then their main role was more on the renewable energy, green technology. Right?
Okay, we have another 8 minutes left in conclusion of our session, so I will go just a little bit quick. There is a question from Hassan. Is switching the motor on and off more efficient than keeping the motor running? The aircon, for example, less energy to keep it on for some time or keep switching on and off whenever hot.
Right. Now this is actually it depends on your cycle time, because if it is one thing that you have to understand, every time you off and on, every time you turn on, you need larger amount of energy to start the motor, okay, because of the load, your moment of inertia, and so on. So if it is the motor is actually going to run, and then you're going to stop for a short period of time, and then you're going to turn on again within a short period of time, then I will advise you not to shut off, not to shut down or switch off. But what you can do is, if it is possible, of course it depends on your system, you can actually have a variable speed drive to run the motor at low speed. That means instead of switching it off, you can run the motor at low speed so that your power consumption will be low. Then when you want to start, it's supposed to be start back, you just increase the speed from a low speed to high speed. In fact, that is what they do with the inverter technology air conditioning system. In fact, instead of the compressor on and off all the time, they control the speed of the compressor so that you don't have a sudden start and stop. So in fact, that is a technique they use to save the energy, right? So the same thing. So it depends on whether you are turning on for a short period. Of course, if your production stops for a long period of time, okay, the percentage within the cycle time, then obviously you switch it off. Obviously you switch it off. But then if it's going to be turned on within a short period of time, don't switch it off, because every time you turn on, you're going to use it.
Okay. There are three questions actually from Vignesh. His first question, I will go one by one. His first question is, as per your slide number 13, assume in design stage, consultant over-designed the pumps without VSD provision in the year 2015. In year 2020, we have a huge budget for chiller plant pumps optimization. Can you share what would be the correct step of optimizing before doing material selection? And how to resize the pump according to operating loading? What type of measurement we should carry out?
Okay. So one thing that you can do is, for the current system, you check it out. You say they assume the design stage consultant over design. Okay, you can actually check this whether it is actually oversized or not by measuring the power. Okay, measuring the power of the motor, the pump system. That means the pump. So what is the power value? So based on the power and looking at the nameplate of the pump, so you can actually find out whether the pump is actually running at light load or not. If it is light load, then you know it is oversized. It is running without VSD, fine. Now, if the pump is actually oversized, then, but if it is new, because it is only 5 years, so I don't think I will ask you to change the pump, because it's going to be costly, because the pump is very new. So yes, you can look into installing the VSD, because that again, you have to look at this, because this is for chiller plant. That means if whether your pump can be run at low speed, because we have many projects that we have done. Yes, you can actually reduce the speed of the pump. Okay, when you reduce the speed of the pump, as I said, you will see a huge savings in terms of energy, power and energy. So in this case, I would say first thing is you try to find out what is the loading condition of the motor by measuring the power, okay, the power at the pump system. Then you know what is the loading condition. Then secondly, see whether I can reduce. Is it possible to reduce the speed of the pump and you won't have any impact on the cooling in your system? If you say yes, okay, then you should be looking at VSD and install a VSD and control the speed. Okay.
Yeah, so quickly for his second question, why the output from VSD? Okay, this is referring to your slide number 21. Why the output from VSD is 360 volt? The motor will not suffer under voltage. How you adjust to 360 volt? Is there any setting in VSD? And then so many questions in one question. Why
okay,
power factor?
No. When you are working with a VSD, you know that the output voltage is actually controlled according to the speed impact, because if induction motor, you know that induction motor, the torque is actually proportional to the voltage. That means you know that I told you that the motor is actually running at a light load, so the torque is actually lower than what is expected. So there's no need for you to apply 400 volt actually, because the torque that is required by the load is low. Yes, if your motor is driving a heavy load, but then you give a low voltage, then yes, high current will flow to the motor. That will actually spoil the motor. But in this case, as you can see that the power factor is also very low, as you mentioned. Why power factor is very low? Because the load is very light. When the load is very light, your power factor will actually be very low. That is another indication why. That is another indication that your load is very light. Okay. So, because it is very light, the VSD will control the voltage. The output voltage will not be safe, for your information. As you control the frequency, you notice that the voltage also will be controlled automatically by the VFD, usually, because this VOF ratio will be maintained. Okay.
Okay, next
question. Due to the economic crisis, what do you think? Any chance of tariff reduction? No way. No way, tariff reduction, no. It will be stagnant for some time. Once everything is okay, then you will notice the tariff will go up. There's no way it's going to go down. There's no way it's going to go down. So I don't see any way that you will never see. I never see any trend of electricity tariff go down. It's always in the uptrend, or it's maintained for some time. So for me, I think personally, no, it's going to go up, but maybe not now. It will take longer time, but then eventually it will go up. Yes.
Would you like to carry on with the following questions, or you would like to?
I'm okay with it if everyone wants me to.
Okay, all right. Because we have quite number of questions. So the next question is coming. Just give me a moment. Okay, the next question is coming from Chan. Before Chan is Mohammed. Okay, sorry. Before Chan is Mohammed Rais. He asked, does incoming power factor will affect motor's efficiency?
Incoming power factor will affect the motor efficiency.
Motor efficiency.
Yeah, obviously. If your plant power factor is low, not only motor, every electrical system efficiency will actually go down, because obviously your current will be higher, and the current is higher, so there will be more losses, and your efficiency will definitely go down. So your plant power factor has to be maintained high, reasonably high. Otherwise, all the system, not only motor, everything will have a low efficiency.
Okay, next question is from Chan. How should we decide whether variable speed drive should be used or not to be used for motor for efficiency, for energy efficiency?
Okay, the variable speed drive is if you have a motor which is currently a motor system which is currently having some kind of the clear one variable load, or they need for example the pump system that I show you, you're actually using a mechanical valve to control the flow. So that's a good example where you should be replacing that with a variable speed drive. Or you have a fan system where you're controlling with a damper, fan flow, air flow, you're controlling with a damper. Some kind of variable load system, which is currently you are achieving the variable load by using some kind of mechanical system, valve, damper, and so on. And this kind of system should be revisited and should be considered going for variable speed drive.
Next question is coming from Mohammed Rais. Can inverter from solar panel and VST from motor coexist on the same line? Since both of these devices will increase some voltage to export out of energy, will these devices be racing to increase voltages?
So inverter for the PV and also this inverter, is it?
Yeah.
Okay. So I think, both are inverter, but then they are actually doing two different things for your information. Well, for the PV is more like you are converting to a voltage, AC voltage, which is required to be connected to the grid. Okay, but inverter that is used for variable frequency drive is actually a variable voltage, variable frequency output. Okay, which is meant to control the torque and the speed. Right. So even though they are inverter, but then they have the different output requirement. Okay, so one is to control both the voltage and the frequency. But the inverter for the PV system, the frequency will be maintained for 50 Hz. Otherwise, you cannot be connecting to the grid. Then the voltage is also maintained the grid voltage to make sure that it can be connected to the grid. So there are two different output requirements. I hope I've answered that question.
The next question is from Aizen, I think. Does IP3 motor creating more running ampere? High standard 3 motor creating more running ampere. I'm not sure.
IE3 motors. Yeah, okay. What happened is, yes, it is true. In fact, the high efficient motors, you will notice that they will be drawing slightly higher current compared to the IE1 motors. But then, again, that depends on the, but then the efficiency will be actually higher. That is one thing that you have to understand. because it's more focused on the efficiency. It means overall power will actually be lower for the given load. Okay, but the difference is not much in terms of current. For the given power, there will be a slight increase in the power, the current. But in terms of efficiency, obviously. But then again, I told you that it's very much depends on the load. I told you that it's very difficult to say that installing the IEEE motors, high efficient motors, the current drawn, provided we are talking about comparing IE1 with the same load, IE3 same load. So yes, there will be a slight difference in the current drawn.
Okay, there is the last question, and I believe afterward I have answered everyone. Okay, this question is there is no name but with an electric energy. What is the maximum ideal efficiency for the controller for BLDC motor? Maximum ideal efficiency for the controller for BLDC motor.
For BLDC motor?
Yeah.
You're talking about BLDC, for what purpose? We need to know what purpose. It depends on the application. Okay? It depends on the application, as I said, because of course the advanced motors like PMSM, all the permanent magnet synchronous motors, and BLDC can give you a better efficiency compared to what you call the induction motors, right? But I don't know. That depends on the application, and I think you cannot be comparing this BLDC and all the advanced motors with the induction motors efficiency directly. Obviously, it's going to give more efficiency compared to.
Sorry, Dr. Gobbi, he has updated PM BLDC motor.
Okay, all right. Yeah. Permanent magnet BLDC motor. That means it's PMSM. Okay. Motors.
So
right? So he's asking about efficiency, correct?
Yeah.
So what is the efficiency of PM BLDC?
Yes.
Okay. As I said, obviously the efficiency, as far as I know, the PM BLDC will give you a better efficiency, and usually these are used for very specific application, right? Very seldom these are used in the industry at the moment, okay, because these are the specific application motors, mostly for electric vehicles and other applications. So the efficiency will be higher. So definitely is higher because the construction itself, that there's a lot of improvement done in terms of improving the torque production, the torque density. There's a lot of improvements compared to induction motors. So the efficiency will be definitely higher, more than 90%, because even the induction motor, we are talking about 90% at the full load condition. So similarly, I think it can be even higher for BLDC. Again, of course, it's depending on the load, because any motor system, it will depend on the load. Okay, depends on the load.
So with this, I think there is no more questions, and I would like to thank everybody for asking questions, and thank you, Dr. Gobbi, for giving very informational and very useful talk in our IEEE PES Day webinar series. I would like to personally thank you on behalf of IEEE PES Malaysia chapter as well. Thank you to Prof for arranging this talk, and Multimedia University. If participants have any more questions, they can directly write to Dr. Gobbi. He will be always available. And we will be having another webinar in the afternoon. If any of you have registered for that, please do join. So with this, this webinar comes to an end. Thank you very much. Thanks to everybody for joining and being with us. Stay home, stay safe.
Thank you for everyone.